we need to use by divide by n square for the normalization of the moments. So this is the definition of the moment for the matrix model and the Dirac model. Henry Lin introduced Bootstrap's method to find the moments of the matrix models. Bootstrap's model has 3 steps. The first step is to find the Schwinger-Dyson equation of the model. And the second step is to find the dimension of the search space. And I will tell you what the search space is for these models. And the last step is a positivity constraint with a cutoff. And that's the last steps comes from the Hamburger moments problem for the single matrix models. So by using these 3 steps, we will find the moments of the matrix models. So let's recall the Hamburger moments problem. Given some numbers, M0, M1, M2, does there exist a positive temporal measure on the real line such that those numbers become the moments of the that measure? And this problem has a solution if and only if the corresponding matrix of the moments is positive semi-definite. So if this matrix is a positive semi-definite, we have a measure with those number as a moment. Sorry. So let's go through the first step. Schwinger-Dyson equations comes from this total derivative. And this is a 0 by using the Stokes theorem. And the derivative in this integral is in the formal case, we can say that this is the cutting an edge from the boundary. So I will tell you what Wij here is. And this is in the general case, we have a multimatrix model. Wij is the word by using those matrices. W is the word by using that matrices, and Ij is the entry of the W. So Wij is the Ij's entry of the matrix W by using those matrices. So let me calculate one Schwinger-Dyson equation in the single matrix model on the board. For instance, if we have just one matrix M, we will take the partial derivative with respect to the Ij entries of M to the power something, let's say L, at Ij entries. This is Wij, e to the power minus V of M, or trace of V of M. And this is the potential, and V is the potential for our case here, dm equals to 0. The summation, all these terms is zeros, but we will sum over I and j. If we take the partial derivative from this one, from the first component, we will end up with the 2. So let me. The equation is following in the single matrix model. The left-hand side comes from the partial derivative of this case, this part, which is the cutting an edge from a boundary with one boundary, and that boundary becomes 2 boundary. The boundary looks like that. And then there is something here. There is something here. If you cut this one, you will get 2 boundary. So that's why we will get 2 trace of h to the power something, or trace of m to the power something. And the right-hand side, when you will cut an edge, which we just attach to the some let's say quadrant or with degree 4. This will increase the size of the boundary, so it's become trace of h to the power L times, let's say, h to the power 3 or v prime of h in that case, or s prime of h. Yeah, this is supposed.
This is a graphical.
Yeah, this is the graphical proof of this. I mean, in the formal set, we can see this. I mean, these are stuff as a cutting an edge from the boundary in the stuff map, in the map.
The upper equation, does it hold for any I and j or just if you
Now,
sum over all I?
all of the, I mean, all of them is 0, then sum of the 0. And yeah, this is like a sum of the zeros.
Okay.
Each one is 0.
Zero and you sum of all zeros.
Yeah.
To get
the
trace.
trace.
But otherwise you will not get trace. Okay.
Usually zero. Then it's usually zero because.
Or just one function and it's
Just
so clear
one
for that.
Yeah, it's Stokes theorem because it's a total derivative.
Then you could make a much stronger statement on the bottom, right? Here you covered it up by summing, take this trace, you're now summing over all entries.
Yeah.
So you could just say the expectation. Right?
Yeah.
Isn't there enough?
You want to reduce all the relations statement.
But we want to find, write it in terms of the mount.
Adding all zeros was it. I don't know, maybe we can also make that
These
statement.
graph pictures assume that sum over all assignments of the vertices graph. That you have to sum over all graphs, all assignments of vertices. So it looks like there is a sum. I and j, well, I don't know. I don't use this myself. So
No, that's.
Cover the trace, but you have everything in terms of traces. Otherwise, we'd have IJs lying around that are not in traces, and we want to compare traces and products. So, those it is ingenious. I mean, this big multivariable.
And if it's unitary invariant, there's really only one formula. That's great. Whole space unitary invariant. It makes it just do the 1-1 entry. Yeah, maybe that's the proof. Unitary invariance is only one term.
But then this guy's not
You mean
necessarily
the
unitary.
proof of vanishing?
Of this is 0 for I and j equal to 1. Then by moving the entries around, it doesn't really matter where you are.
Yeah. No, that's true. That's true.
So that's the proof.
That's true.
Yeah.
I mean, you have a multiple integral. I mean, one of the things is decomposes, and then one of the things is 0. So already. But also, what now that we are discussing, what way to describe also thought recursion also involves this.
Yeah, that's come from the cutting dash.
So there is this combinatorial.
Yeah, commutative proof of this also.
Exactly. Thought recursion. So okay.
And the S was trace of something again. So you have
Yeah.
double trace on the left and double trace on the right. Very efficient.
No, this is no. This is just one.
Just one
Oh
trace.
yeah, this is one.
That's how you get the largest limit.
Because there's.
You got a double trace, and one's only got a single trace. The scaling one of them goes away.
Yeah, because it's become one boundary with more edges, so the degree of increase.
So that's the W11 term, right? Language, right?
But I should put the trace top there because it's kind of confusing. S prime of h, but that one, Thank you for the mention. So let's go to the type 1-0. As we saw, we were looking to solve this model. S of d is g trace d square plus d4. As we calculated before, S tilde of h, in terms of h, we can write it as this form. And the Schwinger-Dyson equations looks like that. I move the higher degree to the left-hand side, and and the rest to the right-hand side. And this summation is the left-hand side of the previous page. I mean, when we have a two trace. So as you can see, because this model is even, odd moments are 0. And if you write it for the first few Schwinger-Dyson equations.
Step 1, how you already?
Yes, I am the large answer.
Yeah.
No.
No, I mean, that's
Yeah, first step was the Schwinger-Dyson equation.
in the previous one. I mean, some crucial factorization you already.
Yeah, I use the factorization theorem, to use the,
Subscript n with all those moments.
yeah,
The factors of n disappear.
yes, exactly.
This factorization only happens in margin.
Yeah, to write this expectation as the product of the expectation by using the cumulative.
Exactly, this concept.
Yeah. Yeah, but yes, by writing this expectation as the product of the expectation plus something, and that one goes to 0 in the large n limit. So this is the general Schwinger-Dyson equation for this potential. If I put L equal to 1, I will get M4 equal 1/8 M0, which is 1 times again also L0, which is 1 times 1 minus 1/2. Because when L is 1, K is also 0.
Oh, yeah.
K is 0, L is 1. This becomes M0, that one also M0. Minus 1/2 GM2 minus 3 M2 squared. So I can write M4 in terms of M2 and G. And also if I go up, also I can write M6 in terms of M4 and M2. So M6 is also can be written just in terms of M2. So the dimension of the search space is 1, and search space is that the number of the moments I need to find all the moments. So this is the dimension of the search space. By having
Geometric series here, that gives you a quadratic equation for the generating function.
yeah.
You can solve this one analytically. It's just an example.
Oh, I see, yeah.
But this is the one I solved.
Yeah.
Okay, yeah.
Like a variation of Hessam.
That's right, yeah.
Yes, exactly.
The simplicity.
So, and let's talk about the positivity concept. As I said before, it comes from the Hamburger moments problem, but we can see it as a positivity of that integral, which can be defined an inner product on the space of the polynomial. So that positivity means that, and this matrix is positive definite. If you want to know what is going on about the positivity, if I apply this positivity to those Schwinger-Dyson equation I have, if I wrote all of them just in terms of M2 and G, and using this positivity, I can.
The M1 is 0, so the odd one.
Yeah, odd one in that case is 0, M1s, M3s. I can get the following solution. As I said, this is the, the green one, the light green contain those orange and also blue or purple color. So it's not a 3 different region. So if you increase the positivity constraints, if you put more constraint by using the, by just change the principal minor metrics of the positivity. if you just increase the size of that principal minor, you will shrink the region. As you go up, the region go to the very narrow line. So this is the solution of the type 1-0 when G is minus.
Sorry, who's the cutoff?
Yeah. I forgot, but it's not 10. It's probably lower also. I mean, it goes to the actual answer very fast. Even if I just check for 10, it's become narrow line.
Cutoff lambda, then you look at moments of low lambda.
Yeah.
You take the corner of your matrix.
Yeah, principal minor. Yeah.
You look at just one, and then these restrictions, usually the equation, some equations,
Cut off get bigger than the restrictions get more.
conjecture.
Very nonlinear.
What is the matrix? So if I write the 4x4 matrix, so bootstraps is like peeling the fruit. Then you just apply this 2x2 matrix. We just peel off one part of the region from the. But if you increase the size, you will peel off more. More of the skin. Yeah, I will. Yeah, tell. That's become the next slide. Yeah. Yeah, you can.
Already for finite, with this kind of strict.
Yeah.
Already there. You see that. You see. Yeah.
Yeah, this is in the large end limit, but the constraint. Cut off the constraint. Yeah, before the phase transition, those, I mean, M2 change with respect to G linearly as we have I mean, Nathan find the formula for that M2 and G, and we also get the same result here, but in the Bootstrap method. There is a, direct line from some point to there, and that's become the actual solution. But before, I mean, what is called after the phase transition, or before, and right hand side of the phase transition is like a curvy shape.
Here, phase transition, linear. The picture that phase transition spectral density is like the density goes for the log. That's other phase transition go after
Thank you. And let's solve the cubic case for the type 1-0 for the warm-up. Then we go to the type 2-0, which is bimatrix model and byte ratio. Again, the S of H looks like that. Is the byte ratio, just one matrix model, but here the odd moments is not 0. So we have odd moments, but we expect that the dimension of the search space increase, but in that case is also 1. If you write the Schwinger-Dyson equations of this model in the large n limit, we will get something like that. But there is a trivial Schwinger-Dyson equation, I would say, because if you put the identity matrix here, m to the power 0, you will get also the Schwinger-Dyson equation. And in that case, the left-hand side becomes 0 because the partial derivative of the identity matrix is 0. The right-hand side become m1 plus m1 square plus g times m2 plus 2m1 and plus m2. When L here is 0, the left-hand side is vanished. m1 times 1 and g times m2 plus 2m1 square plus this is 2m1 square. Yeah. Yes, I put L equals to 0.
What is the second term, m1 squared?
m1 square here.
Is m1?
Yeah, 2m1 square.
The second term is m1 times ml.
Yeah.
0.
So that's become m1. Yeah, the first one is also m.
Okay.
Oh, I think it's so that's the m1 plus m1. Sorry, I made a mistake. So,
We're trying to decide which G's this is positive, right? That's the goal.
what?
Right.
No,
Decide which values are positive.
no. We just want to find what moments we need for this model. If we find m1, we can write m2 just in terms of m1 by using that Schwinger-Dyson equation.
We don't know him. See, when this case is recursive.
Yeah.
You know all harmonic. On the M2 is fixed by. So there is a G. That's the
But here we solve it by m1. Yeah. But here we solve m1. Yeah.
Because it's an
Odd potential.
What I was going to say though is, we will sum the series, Cauchy transform, version, see when you get a positive measure.
Yeah, this one's also solved.
Quadratic equation version. The sync argument is going to depend on G, and sometimes G, you'll be taking the square root of a negative number, so you throw that one away.
This
Yeah.
is also
And,
done, right?
Yeah, this,
Yeah.
we can do this another paper.
Yeah, in the
Okay, so
note.
that's exactly how you solve these recursions.
Yes.
It's right on the money, but yeah, this is just another example.
Yeah.
But then the unsolvable one.
Yeah. This is just warm up for the multimatrix. So the solution of this cubic case, and different color means the different size of the matrix of the moments we put for the constraints. And yeah, as you can see, it's not, symmetry is asymmetry. And the black line, maybe it's not clear here on the board. Yeah. Yeah, it's very small here. So this is the corresponding solution for the cubic case by using the bootstraps.
Where do you have phase cut?
There is no phase
There is
transition.
no phase transition.
Yeah. No phase. Yeah.
I don't think it is.
No.
The Hermitian one-matrix model.
Yeah.
In the cubic setting, there's no phase transition.
No,
I
it's
don't
not.
believe.
So you can do it for any frequent number.
After
Yeah,
some number, the model is become very wild. And I use the Monte Carlo simulation for that things. And the support of the eigenvalues for these number is finite. But when we change G bigger than 0.2 or lower than minus 0.2, the support goes to the all over the R. And I use the Monte Carlo simulation, and it's when it's below the, it's when I just plot the result, is It's from minus 10 billion, just one dot here, all over the place. It's like it's very crazy.
Something like that. It doesn't ever have compact support.
Yeah.
It support the whole real line.
Yeah, it's supposed, and I don't know what's the
So,
meaning of that.
Points G bigger than 0.2, right?
Yeah.
You can have that. No.
We cannot find a solution by using the bootstrap.
There's no positive solution.
Yeah, it's not.
So like, there's no actual row density. Give it an eigenvalue.
Yeah.
This is not
But it might still have. Yeah, there's no phase.
Oh, is this a phase transition?
Actually, I
It's kind of phase transition, different type of.
Yeah.
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 This is different type of the phase transition.
It's a crazy phase, but
But yeah, there's solutions that don't have like a positive measure.
okay, good. Yeah, I'm fine with that.
But yeah, that's what happened.
Yeah. And for the type 2.0 is again the Dirac operator looks like that with those gamma matrices, and ABs are Hermitian matrices. And we will solve it for G trace D square plus D to the power 4. And this is the formula for D trace of D square. Trace of D power 4 is very crazy and ugly. But the good thing is that, again, the model is even, and odd moments with respect to A and B's are zeros. And there is also AB symmetry. If you swap AB, we get the same things. So that helps a lot to solve the Schwinger-Dyson equations. So again, the partition function can be written in terms of A, B, but we have a two matrix here, byte matrix and byte ratio. And the Schwinger-Dyson equations for word A to the power L looks like that, but you can have different word. Let's say A to the power L1, B to the power L2, A to the power L3, and so on. Any word you put there, you will get the Schwinger-Dyson equations. But to see what is this Schwinger-Dyson equation looks like, the simplest case looks like that. And M2 here times ML plus 1 comes from the trace of HS square in trace of AS square, S square, or trace of AS square, trace of BS square. So that's why we have also multiplication of the moments in the right-hand side by M2 to the power times something.
But just MA, this is one trace of A, or you have just one?
Yeah, both the same because A and B are the symmetry.
And if you have just two indices in the last term.
Yeah, this is A to the power L plus 1, B to the power 2. Okay. Or B to the power L plus 1 and A to the, it doesn't matter. But in this case, yeah, we bring all the, because there's a cyclic permutation of the trace, so the number of these components should be even. If it's odd, we can just rotate the matrix and bring it to the first one, and yeah. So that's why we have 2 and 4 here. But the Schwinger-Dyson equation in this case is not closed. I mean, every Schwinger-Dyson equation is like generating more moments for us. But the good thing, if we consider the Schwinger-Dyson equation with word with a degree less than 9, the left-hand side, because it's a partial derivative of that one, the degree become lower. Adding those degree k and L minus k minus 1 become L minus 1. It's less than 8. Okay, so the left-hand side, we cannot have a product of the 2 degree 4 or or more
So
or higher.
There's no closed matrix. We have stuffed two matrix models, let's say. There's no closed.
I mean,
Yeah.
I say completely general stuffed two matrix.
By closed, you mean like solve for all the moments?
I mean, you have a quadratic equation W for one, and the rest are linear equations.
no, that's
No. Go back for a second, Hunter. Because of these AB stuff going on, you have to choose other generating functions for the type A to the L, 1 to E8, right? That would be that one. So you can get a generating function on the left that's W1, but you'd have to invent new ones on the right.
so.
Yeah. We've
Yeah,
played
it's
with
not
this for a long time.
There's no way you, yeah. But if we just have trace AB, yeah, we can have. But
Let me
we have
pick
AB.
from the higher correlation function, let's say, just the first sector, right? ML, rest is one. Don't need all M, L, or A, B, C, D. Just need very specific.
Yeah.
Right? And also from this other one, you just, not the whole information, but just one part.
That's
Is that
true.
right?
That's true, but the separating them is difficult.
I mean,
Yeah.
I'm completely, yeah, you're right.
It may not be impossible, but
Yeah.
yeah, that's really you just get those like that, and I think the rest follow.
So there is no, in the left hand side, there is no product of the 2 degree 4 and higher. And the right hand side, we just have the M2 times some moments. So if we take M2 as a formal coefficient, we have a SLE system of linear equation for Schwinger-Dyson equation of order 9 and less. So if you solve this model just in terms of G and M2 and put it to the next Schwinger-Dyson equation, again we have those are become again. I mean, the left-hand side is not product of the 2 moments with more than 4 degree again. One is M2, one is something else. So it's become again linear equations, and we can solve it again and put it to the next Schwinger-Dyson equation. And if you do it, we will end up with those relations. So M4, just in terms of the G and M2, M2, G and M2, again, all the moments we can write in terms of the M2. And by this method, we, yes, I should say that the number of the non-trivial moments in the loop equations with less than lengths more than 9 is less than the number of non-zero loop equations. That's why if you do it again, you can solve the SLE, and you will have those relations for the moments. We calculated up to degree 12 or 14, but I just put up to degree 6 or maybe 8. Yeah. Yeah.
Size you want.
Any size, yeah. Just
Yeah.
machine is work. Yeah, we found some pattern. Yeah.
See some definite powers.
Yeah. Well,
So
Yeah.
you should rescale by 2. That's the first thing. Get rid of it.
Yeah. Yeah, at the beginning, if you choose G over 8, yeah, or yeah, that would be.
There is a pattern, but it's not good.
And there's only one minus sign.
And some of them has minus, you know, for example, M42 has 2 minus signs.
Oh no, those are the fourth sign, but the ones that only have one.
Yeah.
Yeah, there's one on the G function, third from the right, there's one on the first.
Oh, missed that.
Yeah.
Okay. So that's an odd power. So G goes to minus G. No, that doesn't.
It's fun to just look at.
Yes.
You see something, and then it turns out that it's kind of something, but not quite what you thought.
Yeah.
The ultimate thing is you turn.
Yes.
Flip, reverse, and hopefully at some point
maybe nobody want to show them the relation.
If you look at the formula, you can see that M4 is 2 times M22 plus M1111. If I am right. Yeah, and M6 is twice of M42 plus twice of M3111 plus M2121, if I am remember correctly. And yeah, there is some formula for M4, M6, and M8, just in terms of.
Now the coefficients are all positive and no G's.
Yeah, yeah, it's so nice.
But of course, the number of columns is going up. It's only 3 columns, right?
Or yeah.
Yeah.
3 columns. That's the most it goes up to. Right.
Yes.
Yeah. I think other that were the same. On that we're looked alike but weren't quite alike. That's for higher. There could be others.
Yes, yes. But we use A and B symmetries, but for the gamma matrices or this. Yeah, there are some other relations. For instance, if you saw these two numbers is just different from M2 square. So M4 is M22 plus M2 square. Or yeah, we can find the relation between M22 and also M2 and this number. So yeah, there are some patterns there, but we don't know how. But some of them, yeah. Yeah, we have find some graphical interpretation for these formulas by changing the color of the edge of some polygons.
The left-hand side, if you get to the formal version, is counting quadrangles or counting maps from those guys, up maps with a boundary of -4 of one color.
Yeah.
And somehow you're getting this equation is defined by ejections between sets, but
yeah.
Like graphically, how do you like it's
it's hard to describe. But,
Looks like a nice problem.
Yes. So yeah,
So
this
where
is.
was the sign?
When you write it like that, the signs are gone. All positive.
We can think, but where are you writing? But M3111. There's a sign.
Yep.
Negative. Yeah.
You have not for this a graphical interpretation in terms of map for M11?
So you mean how to get from M2?
Yeah.
Yeah, we don't know about that.
Yeah.
That's
That's we are taking.
These are the same relations, but just written in a way that nicer. So if we can figure that one out, I don't know how we can actually question and the negatives, of course.
But you're looking at two metrics, right? Where you have colors on the map.
Yeah. You have to glue the same colors to each other.
Yeah. And do you distinguish two different M2s?
No, because the M2 with A is the same as M2 with.
Okay.
The symmetric, potential symmetric.
There's also like in this model this 8 where
No,
you don't have.
there's no AD interaction. Yeah, there's no just trace of AD up there. It's good for proving that a trace AD is harder, but it does change things quite a bit.
So A and B does not
They interact differently. Yeah. Is the reason that nice closed loop equation for the AD model is because it's just a higher interaction. But when you have higher interaction, it's more complicated. Just simplify.
And we find the Dirac moments also, because we have some relation between the H and D, A, B, and D. So we can find the Dirac moments of this of Dirac ensemble. D2, D4, D6 looks like that, but the formula for D8 is very complicated, and we're using the chord diagram. Yeah, it will take time to find the formula just in terms of H to find, to write the moments of the Dirac in terms of the moments of H. But we just stop at D6. Then the positivity constraints. Again, if you make a set with all the possible words with A and B, and these set become the basis of the vector space. The inner product by using the 1/n trace of the word transpose times the other word. Yeah, it's become positive definite. So here MPQ is 1/n trace of WP star conjugate WQ. It means that the transpose of the word. If you have a ABA, it's become ABA AB2 A3 star become A3 B2A. So yeah, this means the positivity of this matrix. So for instance, for just taking empty word AB, AA, AB, EB, if you write the basis over there and find the matrix of that quadratic form in that basis, you will get the following matrix. So this matrix should be positive. Yes. Yeah, all.
Or even if there's an odd number of A's.
Yeah, I mean.
Also MAB also 0, yeah.
Yeah.
So the solution of the type 2, 0, because we write all the moments in terms of M2, we have just one-dimensional search space. Again, by putting more constraints, we get the narrowing region. So this purple line is the very close solution to the answer, the actual answer. Again, the phase transition in this model appears around -3 by the Monte Carlo simulations. So it looks linear before the phase transition, but there is no proof because we don't have the actual, actual relation between M2 and G. But it seems to be linear before the phase transition. So this is the type 2-0. We can observe the Bootstrap method also as is SDP. It means that the minimizing of the CI, WI here, WI are moments, and we can write the Schwinger-Dyson equations and bring all the quadratic part to the left-hand side, all the rest to the right-hand side. And AIJ is the matrix of the coefficients. I mean, the coefficients of those Schwinger-Dyson equations, and subject to this loop equation with the positivity constraint, SDP. We have SDP in many programming, such as Python or MATLAB. I don't know. Mathematica has SDP, probably has. I'm not sure. So recently, Kozakov and Zheng developed the idea of bootstraps and relaxed the nonlinear equation of the linear ones. As you can see, the Schwinger-Dyson equation is quadratic. On the left-hand side is the quadratic part. So they introduce the new variable, new independent variable xij. By xij is product of the moment I times j. So by those change of variable and the positivity of the relaxed matrix, the SDP we had before have the same solution with this SDP, minimizing, but Schwinger-Dyson equation changed to the those linear equations and the positivity of the relaxation matrix, and this is also positivity of correlation matrix we have. So this relaxing bootstraps, because those equations are linear, is quite faster than the previous one. So the result is also much better. So yeah, they recently developed this idea to the relaxed bootstraps, and yeah, that's goes to conclusion. Bootstraps offer never before opportunity to study Dirac ensemble, and Monte Carlo simulation is severely limited of matrix size, because if the size of the matrix H is 20, size of the Dirac operator become 800 by 800. If you run the Monte Carlo simulation to find the eigenvalues, each sample you take for the H to make it Dirac ensemble, then find the eigenvalues, it will take time. But by using this method, by using the bootstrap, you can find the solution much better and faster with respect to Monte Carlo simulation. And maybe we will apply bootstrap in the signature 3 or more, but those become much more complicated because the Schwinger-Dyson of those models is quite hard. But yeah, it's possible to do that. And we want to find the reconstructing the eigenvalue distribution of both Diracs and random matrix also, because we have the moments we may able to construct the eigenvalue distributions, maybe subject to maximizing the entropy integral of the, let's say, the rho of x, log of rho of x, minus of this guy, d of x. If you have a moment, find the somehow distribution, this become the maximization of the entropy. If I call entropy, I mean, among all the answer, the ones with good result, with has a maximization of the entropy. I mean, this value should be higher if you want to get a good result. But yeah, we want to find the eigenvalue distribution by using the bootstraps method. But in the Monte Carlo simulation, you have those distributions. You can find the moments. I mean, you can find the phase transition. You can do more, but bootstraps is also, yeah, it's better to find the moments. Maybe we can find the eigenvalue distribution by using the bootstraps. Or maybe the phase transition by checking for what value of G these become. I mean, those relations become linear. And yeah, and we want to find the SDEs. I mean, Schwinger-Dyson equation is strictly in terms of the Dirac moments for any random geometry and Dirac ensembles, because we have the Schwinger-Dyson equation just in terms of H, but it's very nice. It's very good to have the Schwinger-Dyson just in terms of P. But yeah, we couldn't get it so far. But yeah, we will try it. And that's it. And these are a good reference for this talk, Barrett and Glaser. In the Monte Carlo simulation, they find the phase transition in the different type of the Dirac ensembles, and also find the eigenvalue distribution. Here, really, in the bootstraps method, that's the first time they use bootstraps in the matrix model, in the random matrix model. And the paper of Nasud Khalkhali and Nathan, also mentioned by the Nathan for the phase transition in the type 1-0 in the last talk. And because of Kof and Zheng, they developed the bootstraps in the relaxing bootstraps And Carlos Perez Sanchez also completing the spectral action, I mean, trace of the power of D by using the chord diagram. And that's very nice paper to read. And the last one is the paper I just presented. And that's it. Any questions?
I have one comment. So now I think it's clear what do this Harishchandra by this bootstrap.
Bootstrap.
Because I mean methods about some.
Yeah, it's very powerful, is it? Yeah. Yeah. Whenever we have some constraints, we have positivity.
I think someone's done it for 10 model. I mean, yeah, but
I think so. I think I saw a paper.
really, but I'm not sure.
I'm sure they can do all tensor models.
But one thing I didn't understand.
Of course, yeah.
One thing I didn't understand. Yeah, one thing I didn't understand is Kazakov idea. I mean, so you said they replace a quadratic term, they declare it to be just one. What do we gain by renaming this variable?
Yeah.
What was the gain in the
Because the region to find, I mean, for the SDP should be convex, but this quadratic equation is not convex. So they try to just replace it with the linear ones. So, and then they claim that by using the new variable xij as a wi times wj and using the positivity of the this matrix, as you can see, if xij's become wi times wj in the answer, the rank of this matrix become 1. So it's like the critical point of the solution, maybe the ones with the.
So the observation is that, say, is the result in is.
Yes. No, they also apply the positivity constraint and replace the Schwinger-Dyson equation by these two conditions, linear ones and the positivity of the relaxation. So because we have the they use in a stats thing, a stats. They use the a statistician, So because in this SDP we have more variable, we have and they saw that the result of this relaxation bootstraps is get the same result when they have this method. So they didn't prove that this is exactly it's the same with this SDP, but but in the experimentally they saw that the result is also valid in the usual SDP.
By the way, also on this paper, also
Lattice means story, So bootstraps.
also the
Is this possible to apply bootstraps method to the free probability? Because
I don't know.
because there is a positivity when you have a threshold.
For typical ensemble. Positivity.
Yeah, but
I don't know. What question is what ensembles want to know about?
the ones that they haven't solved.
Yeah, already solved.
Take it out.
Volatility and some sort of recursive relationship.
Yeah.
Draw. We don't know.
But usually it's fast. Yeah, it's converged to the actual solution very fast.
Moment.
Mhm.
So,
Yes.
so that was just the expectation of trace of the square times trace of the square, right?
Not two trace. This is like one
So that was
on an expectation of the trace of a square b square. Limit of angles.
In the backstory of the limit, the trace is split.
remind me again of what you said.
A, B are Hermitian matrices, and they are independent.
They're independent.
Yeah, they are independent. Independent.
If the variables are defined.
Yeah, there is, okay, well then, I mean, those things factor, right? And then the factor is the product of the traces plus the covariance, which is a 1 over n squared term. Well, assuming that formally. So, I mean, you can always write the product as an expectation of the trace of A, trace of then plus the covariance. So it drops down to a lower, that gives you the next term down in expansion. So there's
Then you have two trays.
fluctuation loss, but the next thing's down a lower order. I guess I'm a little why you can have an M4 and an M2, 2 living in the same space. They should be different.
I don't think they're the.
Yeah. So the entries, I mean, you have then matrices, and that was
Yeah, but they're piling on it. The potential is.
Yeah.
There's those extremes.
Yeah, they are mixed up.
You have the entries of the matrix and
And-
talking about the matrix.
Yeah, integrating over two different sets of variables. Right?
Yeah.
A is some sling and B is something else, which means.
Oh,
I mean, I'm talking about is
No,
independent.
they are related,
But
but
the joint PDF is. They're not.
No, just, I mean, like normally they say you take the classical Louise or Boycott road that, well, that was easy, but the sum of independent Stirling and variant those the term is asymptotically traced, you can use but it's crucial. You have A and B material. One of the variant. Then you can use the value. So yeah, I guess I don't. They talk offline.
Why do they call this? What's the relation between?
Because you go back to the moments and then come back again, or is that it?
Bootstrap, bootstrap is something, you know, you pulls by pulling something. Out, you know, it's just, it goes against common sense.
You can lift yourself by your
Yeah,
own
but,
bootstrap.
yeah,
but it has nothing to do with the
physics.
Statistics.
No, it does. It does. Statistics is also
They
saying
call it
that,
bootstrap and statistics, right?
yeah, but the originally started in physics, 1960. So it was done by coined, I think, by American physicist Peter Chu. So his idea was that, well, we don't know anything about you know, strong impact. So what we can do is that just push off this. They had some sort of, it was called Bootstrap program. But then it was abandoned because Yang-Mills theory was covered and usually. They were giving up on primary. But then it was revived. So was revived 10 years ago. Conformal field theory in 1994. This was done by Rishkov in Bootstrap, similar ideas. And so really very stop. Because conformal group very small, small. A lot of constraints, so all the constraints. This Q dimension. And it's revived after. With statistic. But it's the same idea. I mean, it's like you're using not. Yeah, of course. Sure.
We're just model basically,
Yeah,
so
yeah.
like
The paper of him, it is this shoes.
yeah, he's got he has an actual picture of
Himself by his
Hang on,
shoestring.
trickier than okay, well let's thank again. Yeah, well let's see,